Good day, everyone. In today's video, we'll be exploring how three-phase electricity works, and how its voltage curves follow a sinusoidal path. We'll also delve into the importance of the square root of 3, when calculating three-phase power. Three-phase power can be supplied either from the grid through a mains connection, or generated independently, using an electricity generator. Regardless of the source, the generation process is largely the same, typically involving a generator or alternator, with star-connected windings. Star-connected windings are often preferred in generators, for both technical and economic reasons. Technically, star connections allow for a neutral point, which is essential for handling unbalanced loads in three-phase systems. Additionally, the phase voltage in a star-connected generator is 1.732 times, or the square root of 3 times lower than the line voltage, unlike delta-connected windings, where the phase and line voltages are the same. So, why is this important? Using star connections ensures efficient voltage regulation, and offers a better balance when dealing with varying load conditions. Continuing on, the star-connected winding has an additional advantage. It reduces the cost of insulation, giving it an economical edge over the delta-connected configuration. In a star connection, the neutral line is typically grounded, using a neutral grounding resistor. This resistor serves an important purpose. It limits the ground fault current to a safe level, ensuring that all the connected equipment is protected from damage. Now, let's talk about how electricity is generated. If we rotate the magnetic field on the rotor of a generator, an electromotive force, commonly known as the voltage, is induced in the stator windings. In this example, we are showing a generator with 6 poles, but for simplicity, let's consider a basic 3-pole generator. To better understand this, let's look at the coil voltages of the phase windings, with terminals U1, V1, and W1 marked. As the magnet rotates, the voltage generated in each coil will rise and fall. When the magnet is perpendicular to the coil, the voltage generated in that coil becomes 0. This happens because, at a 90-degree angle, the magnetic field has no effect on the winding. It's like, the field is neutral to the coil, at that point. Let's take the red phase as a reference point. After the magnet passes the point where the voltage is 0, the voltage reverses direction, and so does the current flow along that line. The maximum voltage is generated when the north end of the magnet reaches the relevant winding pole. As the magnet completes one full rotation, the voltage generated on a phase winding reaches its peak twice, once in the positive direction, and once in the negative. These opposing peaks are what we refer to as the maximum and minimum values. In the current animation, the rotor is spinning very slowly, at half a revolution per second. However, in a real-world scenario, a three-phase, 3-pole generator supplying power at a frequency of 50 Hz would be rotating at 3000 RPM, or 50 revolutions per second. Now, let's increase the rotor speed to 2.5 revolutions per second, which is equivalent to 150 RPM. To achieve the actual operational speed of 50 revolutions per second, that is 3000 RPM, the rotor speed needs to be increased by another 20 times more from this point. Monitoring the speed of voltage changes with the naked eye is impossible due to how fast they occur. Here, the three-phase voltages are shown 120 degrees apart, and their sinusoidal waveform behavior is displayed at a slower speed for clarity. As mentioned earlier, the actual speed in a real-world system would be 50 sine wave cycles per second, which is far too fast to observe directly. This highlights how rapidly the generated voltage alternates, and explains why we use the RMS or the root mean square value of it, for calculating alternating current electricity. The RMS value gives us a more practical measure of voltage for calculations, as it represents the equivalent DC voltage that would produce the same amount of power. It's also important to note that for a 6-pole generator, the rotor speed is 1500 RPM. Additionally, the supply voltage frequency is 50 Hz in Europe and many other countries, while in North America and parts of Japan, it's 60 Hz. Now, let's take a closer look at how a single-phase voltage sine wave progresses over time, in slow motion. Now, let's bring the RMS voltage into the graph. Although single-phase voltage fluctuates rapidly between plus 325 volts and minus 325 volts, we use 230 volts as the constant RMS voltage for single-phase power calculations. This is because the RMS value represents the effective voltage of all the fluctuating values. The equation for single phase power is simple and is P equals V multiplied by I multiplied by cos phi, where P is the power in watts, typically listed on the machine's nameplate. V is the voltage, which is 230 volts for single phase power. I is the current, measured in amperes, which we may need to calculate using this equation based on the rated power in watts. The power factor, cos phi, is also typically listed on the nameplate of the machine. For three-phase power, the concept is slightly different. The yellow and blue phases lag behind the red phase by 120 degrees and 240 degrees, respectively. All three-phase voltages advance along their sinusoidal wave paths, maintaining a constant 120-degree phase separation from one another. This phase difference is key to how three-phase power is transmitted and utilized efficiently. In a three-phase system, each individual phase voltage fluctuates between plus 325 volts and minus 325 volts, just like in single phase. However, if you measure the voltage between two phases, you'll get 400 volts. Let's pause the voltage curves when the blue phase reaches zero. At this moment, the yellow and red phases have equal but opposite values. One is positive, and the other is negative, resulting in a total voltage of zero. In fact, at any given point in time, the sum of the three-phase voltages is always zero. This is crucial for understanding how a balanced three-phase system works. When a three-phase induction motor, or any other balanced three-phase load is connected, the current on each of the three lines behaves in the same way as the voltage. As a result, the total current flowing through the three lines is also zero, meaning no current flows through the neutral wire in a balanced system. Now, for three-phase power calculation, let's start with the star connection. In this configuration, each phase coil experiences 230 volts, and the voltage between any two lines is consistently 400 volts. As mentioned earlier, the line voltage in a star connection is equal to the phase voltage multiplied by the square root of 3. Additionally, in a star connection, the line current is equal to the phase current. When calculating three-phase power, you could apply the single-phase power equation to each of the three phases individually, and then multiply the result by 3. The basic single-phase equation is V, that is phase voltage, multiplied by I, that is phase current, and multiplied by the power factor, cos phi. To find the total power in a three-phase system, you multiply this by 3. However, for three-phase power between the lines, you'll need to replace the phase voltage V with the line voltage V divided by square root of 3. The phase current I phase can be directly replaced by the line current, I line. Now, if we expand the 3 in the equation, we can write it as square root of 3 multiplied by square root of 3. Then, 1 square root of 3 cancels out, leaving only 1 square root of 3 in the final equation for three-phase power. The result is, P, the total three-phase power equals square root of 3 multiplied by V line, multiplied by I line, multiplied by cos phi. This is the formula used to calculate the total power in a three-phase system, where V line is the line voltage, I line is the line current, and cos phi is the power factor. Now, let's consider the case where the three-phase lines are delta connected. In this configuration, the line voltage V line is the same as the coil voltage, or V phase. However, the line current I line is equal to the phase current I phase, multiplied by the square root of 3. To calculate three-phase power in a delta connection, we can apply the single-phase power equation to each of the three individual phases, and then multiply by 3 to find the total power. The single-phase power equation is P equals V phase multiplied by I phase, multiplied by cos phi. When calculating the total three-phase power, we multiply this by 3, yielding P total equals 3 multiplied by V phase, multiplied by I phase, multiplied by cos phi. Next, we adjust this equation for the line conditions. Since V phase is equal to V line in a delta connection, we can replace V phase with V line directly. However, I phase will be replaced by I line divided by square root of 3. Once again, we can expand the factor of 3, as square root of 3 multiplied by square root of 3. This allows us to cancel 1 square root of 3 from the top, with the 1 in the denominator, just like we did with the star connection. Once again, we are left with just 1 square root of 3 on top. Therefore, the final equation for three-phase power is P equals square root of 3 multiplied by V line, multiplied by I line, multiplied by cos phi. Now you can see where the square root of 3 factor comes from in three-phase AC power calculations. It's a fundamental part of the relationship between line and phase voltages and currents in both star and delta configurations. If you found this video helpful, please consider subscribing to the channel for more insights on electrical concepts and power systems. Thank you for watching.